In the next 20 minutes or so, I would like to talk to you about how important it is to properly seal the borehole that deep isolation uses to dispose of nuclear waste. I will briefly describe the deep borehole repository system, then the computer model we developed to analyze the migration of radionuclides from the horizontal disposal section to a drinking water aquifer, and how the safety of the repository, or the exposure dose, is affected by how well we seal the borehole. This is a continuation of our previous safety analysis work, but this time we focus on the curved and vertical access hole, which is often considered a potential leakage pathway for the fast release of radionuclides to the land surface. Let me put today's topic in context to the technical work that Deep Isolation has presented in a previous webinar and published in a series of technical articles. In a webinar in May of last year, we gave you an overview of our generic work on long-term repository safety. We introduced the general borehole disposal concept, described the main components of the repository system and how they are represented and integrated in our conceptual model. We then discussed the results of our initial safety calculations. This included a deterministic reference scenario, but also sensitivity analysis, disruptive events, and a probabilistic safety assessment. You can view this technical presentation and the question and answer session that followed by going to Deep Isolation's website. Today, we will examine the role of an ineffective borehole seal on long-term repository safety. This study is based on a similar conceptual model as before and using a similar modeling approach and performance measure. The technical details of this analysis can be found in an open access peer-reviewed journal article. To provide some background, let me briefly describe the repository system. We are looking at a repository that consists of multiple boreholes that are drilled parallel to each other. Starting at the land surface, the vertical section of the access hole penetrates the aquifer and what we refer to as the overburden, which is the formation above the host rock. At an appropriate kickoff point, the borehole starts to gently curve until it becomes horizontal at a targeted repository depth within a suitable host rock. For the current analysis, the host rock is a tight shale or clay stone. Waste canisters are then placed end to end within the horizontal disposal section. Each canister holds a single spent nuclear fuel assembly. The repository is then closed by backfilling the curved and vertical access section of the borehole. The main topic of this webinar is the safety function of this backfill. The question of how much we need to rely on proper sealing, should we need to make sure that no water, potentially with radionuclides dissolved in it, flows along the borehole. Even though we are considering the effect of multiple parallel boreholes, it is actually sufficient to look at the single vertical slice, a symmetry cell, which contains only one of these boreholes. So the three-dimensional computer model you will see in the following slides shows only one of these vertical symmetry cells. I also want to briefly summarize how the environment at depth looks like. Our shale formation or any other suitable host rock is very tight, so it is difficult for water to flow through it. This is the main reason why the water in the pore space of the host rock is expected to be very old. If we find such old water, that would indicate that the host rock has been isolated from the near-surface hydrological system for a very long time. The water pressure at depth will be high, so the water won't start to boil despite the fact that the waste will generate considerable amounts of heat. We also expect to be in a geochemically reducing environment as opposed to an oxidizing environment, which is important as it affects corrosion rates, the solubility and mobility of radionuclides. The disposal section of the borehole will be far from the surface, which gives us safety in depth, mainly because the long travel times allow the radionuclides to decay, but also because the environment at such depths is relatively stable and not affected by processes and events occurring at or near the land surface. The previous and current safety calculations are based on a computer model that integrates the key components of the entire repository system. Let's briefly look at the elements of this integrated model. The so-called source term model is based on the waste inventory. It accounts for canister breach, which initiates the slow degradation of the waste, followed by the release of radionuclides into the borehole and the near field of the repository. The waste also generates decay heat, which is accounted for in the model. Once released from the canisters, the radionuclides are transported along the backfilled borehole as well as into the host rock, from where they migrate through the geosphere, mainly by slow diffusion, but also carried by the flowing groundwater, which is eventually drawn into a drinking water well. The biosphere model then looks at the pathways through which humans may be exposed to contaminated groundwater and thus the residual radioactivity from the waste. It is this radiological exposure dose that is the ultimate performance measure of safety. It allows us to comment on the question if and by how much the maximum dose or the peak dose is below a standard that is considered safe. Exposure dose is given in rems or sieverts per year, which is a measure of the health effects of low levels of ionizing radiation on the human body. Again, we use this integrated model to examine whether a poorly sealed access hole will significantly reduce this safety margin. Why did Deep Isolation decide to look into borehole sealing? First, any geological formation that can be considered suitable to host a nuclear waste repository is, almost by definition, essentially impermeable. This is in contrast to the access hole and the repository itself, which are initially open structures. If left open, the borehole may become a flow path for the fast release of radionuclides. It seems obvious that such potential leakage pathways need to be sealed. Many borehole sealing technologies have been developed and tested, mainly by the oil, gas and geothermal industries, but also for natural gas storage systems, geologic carbon sequestration, and also specifically for nuclear waste applications. The effectiveness of such seals can be tested, but it is very challenging to demonstrate or prove that such seals will be tight over millions of years. Now, a borehole seal may not have been installed properly, or it may become ineffective with time because of chemical degradation and mechanical and thermal stresses. Borehole seals that are compromised in any way are generally considered a safety risk. Nuclear waste organizations have put great efforts into designing and testing the backfilling, plugging, and sealing of underground openings, including access tunnels, ventilation shafts, deposition chambers, monitoring boreholes, and specifically waste disposal boreholes. A large number of physical experiments and associated laboratory tests and numerical analysis have been performed to understand the behavior of such seals and to optimize them. However, there are surprisingly few studies that actually look at the impact that the compromised seal has on the ultimate repository performance, which is measured by the exposure dose. To fill this gap, Deep Isolation decided to examine the consequences of a poorly sealed borehole rather than the effectiveness of a well-sealed borehole. Before we look at the impacts of a poorly sealed borehole, I want to emphasize that any deep isolation borehole will be properly sealed. We don't have the time today to review all the materials and methods that have been proposed or are actually used to backfill and seal boreholes, but they include bentonite, cement, various grouts, oil-based materials, metal plugs, cross-linking polymers, various packer systems, pellets, high-density support matrices, or the rock itself, which can be heated up until it melts and then later recrystallizes. In the United States, Sandia National Laboratories has reviewed most of these sealing methods and has proposed a design to make sure the vertical access hole is properly closed and does not become a leakage pathway for radionuclides. Deep isolation could use plugs that are strategically placed for greatest effect, for example, between the last waste canister and the curved section of the access hole, and then backfill the borehole with a self-sealing material or a sequence similar to that proposed by Sandia and others. Let's briefly talk about sealing requirements by noting that the purpose of a seal varies depending on where we are within the borehole. For example, the top section of the borehole needs to be sealed to protect the aquifer and to prevent inadvertent or malicious human intrusion. The middle section of the vertical access hole is mainly sealed to plug so-called feed or thief zones, which are zones of high permeability where fluids may readily flow into or out of the borehole. In the host rock, the borehole could be backfilled to reduce or prevent axial flow of contaminated water out of the waste disposal section. Finally, waste retrievability requirements must be considered when designing seals. This is a topic that goes beyond what we can discuss here, but it is worth mentioning that most regulations and recommendations limit the retrievability period to the time before a repository is plugged, sealed, or backfilled. Deep isolation has demonstrated that waste canisters can be retrieved from open boreholes, but is most likely also possible, with greater effort and higher costs, to retrieve canisters from a closed borehole, should that be considered desirable or necessary. I want to reiterate that our study did not examine the performance of these sealing materials, but in contrast, we wanted to know what happens if the seals have failed. To answer this question, we performed generic safety calculations, assuming that the borehole is either well sealed, which serves as the reference case, or poorly sealed, which is our conservative bounding case. The poorly sealed case does not assume that the borehole remains open for 1,000,000 years, but that its backfill or seal has crumbled or is cracked or detached from the borehole wall or otherwise degraded to the point where it has a permeability of beach sand. Sand would pose little resistance to contaminated water being pushed up the borehole. Besides the property of the backfill, we also need to talk about the second important factor, the potential driving force that needs to be present to push contaminated water along and up the borehole. It is surprisingly difficult to come up with scenarios that generate a sufficiently strong upward driving force. The main reason for this difficulty is the fact that the repository is in a tight formation, which means there is simply not enough mobile water available to push out the contaminated groundwater and to sustain that push over long times. To come up with an abundant supply of overpressured water, we needed two events to occur. First, we assumed that a large earthquake occurs and reactivates two faults that intersect the disposal section of the repository and at the same time destroys the canisters. Second, we assume that the brine in the formation beneath the repository is overpressured and that this overpressure does not diminish despite some of the brine leaking out through the faults. The right fault here pushes up brine into the poorly sealed repository and up the access hole into the aquifer, where it eventually will be drawn into the drinking water well. We refer to this as the two-fault scenario, but we realized that a case with a single short fault may be even more relevant, because the pressure cannot readily dissipate into the more permeable overburden as it can in the two-phase scenario, but the brine has to flow along the poorly sealed borehole, pushing out the radionuclides. At this point, we are not concerned about the probability of either of these scenarios, which will be very low. We just want to look at the consequences should they actually occur. This sequence of figures shows how one of the longest lived and most mobile radionuclides, iodine-129, migrates from the repository into the host rock and from there into the overburden through the faults and, most notably, along the poorly sealed access hole. Let's zoom into the curved section of the access hole, where we see, as expected, that overpressured brine chooses the path of least resistance and pushes out contaminated groundwater into the poorly sealed access hole. We also see that some of the iodine diffuses radially out into the host rock, and once the leading edge of the plume reaches the more permeable overburden, this radial loss into the rock essentially stops the further migration of iodine along the borehole. In fact, we see that most of the radionuclides flows along the faults, which are much bigger structures than our small diameter access hole. And it is this large transport through the geosphere that controls the total system behavior and, as we will see in a minute, dominates the exposure dose. Yes, we do see iodine eventually coming up the borehole into the aquifer, but most of this iodine did not flow along the vertical access hole, but through the fault and was then sucked into the borehole, which is under pressure because of the continuous pumping of groundwater from the nearby drinking water well. Let's look at these phenomena again for the scenario with only one fault. Recall that in the one fault scenario, the earthquake generates the highest overpressure in the repository because the fault terminates in the tight host rock, with the borehole being the preferred or only escape route for the pressurized brine coming up the fault. It also has the longest sweep length. The fault intersects the repository near its dead end and pushes contaminated water from all waste canisters towards the access hole. Once the pressurized water reaches the more permeable overburden, it flows radially out, away from the borehole, and the pressure dissipates quickly. This effect is also clearly seen by the cone-shaped plume of iodine, which is the result of radial, advective and diffusive radionuclide losses from the access hole into the overburden, again drastically slowing down the upward flow of contaminated water along the borehole. It should be noted that the cross-section of the borehole is very, very small in comparison to the cylindrical area available for these radial losses of water and radionuclides I just talked about. And the size of the access hole is much, much smaller than the overall repository footprint. After about 1 million years, radionuclides enter the aquifer at very low concentrations over this entire footprint. In comparison to that, the tiny borehole cross-section is insignificant, even if radionuclides flow at an increased rate because of poor borehole sealing. We are now ready to answer our main question. How does poor sealing of the borehole impact the safety of the repository, where we measure safety by the maximum annual exposure dose, as shown by these curves? The red curve is the result from our nominal scenario, with a well-sealed borehole and no earthquakes happening. We see that the peak dose of 0.01 millirams per year is reached after about 1.5 million years. This dose is about 1,000 times below a typical dose standard of 10 millirams or 0.1 millisieverts per year. Our conservatively designed disruptive event, an earthquake that reactivates two faults which intersect the repository, moves the dose curves a little bit to the left and up. The peak dose occurs now after 800,000 years, and it is slightly higher, but still well below the stringent dose standard. For our analysis, it is important to realize that this shift in the dose curve is not caused by the leakage through the borehole, but by the presence and preferential flow through the two faults. What we need to focus on is the difference between the well-sealed and the poorly sealed boreholes, between the green curve and the blue curve. These differences are barely visible on this plot, and they are truly insignificant. The same conclusion can be drawn for the single fault scenario. Recall that the single fault case was designed to maximize the negative effects of a poor borehole seal. The light blue curve is for a well-designed borehole, well-sealed borehole. It is very close to the red curve of the nominal scenario. Even the presence of a fault that intersects the repository is barely visible, because the fault terminates within the host rock and therefore does not form a preferential flow path. The orange curve indicates that if the borehole is poorly sealed, some radionuclides arrive at the drinking water well a little bit earlier, however at exceedingly small concentrations. The relevant peak dose, however, is not affected by the quality of the borehole seal, supporting our previous conclusion. Let me summarize our work and what we have learned from it. We have numerically evaluated radionuclide releases through the poorly sealed borehole, making conservative assumptions specifically about the existence and prevalence of large driving forces along the borehole. The analysis suggests that the contributions from borehole leakage to the annual exposure dose are insignificant. The main explanations for these results lie in a few simple geometrical facts. The borehole diameter is very small in comparison to the borehole length, so that radial losses of water and radionuclides into the surrounding rock outweigh and drastically reduce axial transport along the borehole. The borehole cross-section is also extremely small in comparison to the repository footprint available for radionuclide transport. The total leakage from the repository to the aquifer is very, very small. The leakage through the borehole, even if poorly sealed, is insignificant. And thirdly, the overall geometry of the horizontal borehole repository layout is also beneficial, with a change in orientation and an offset of a few hundred meters from the horizontal disposal section to the vertical access hole. I think the fact that the small impact of poor borehole sealing is related to geometry is a very good outcome, because there is essentially no uncertainty about the geometry of the borehole and the repository layout. And these basic geometrical facts are not going to change even over very long time periods. So the conclusions can be considered quite robust. Finally, strong vertical driving forces are difficult to emerge in the deep subsurface, and the source of water that would sustain them over a long time period is difficult to find in a suitable host rock of low permeability. The fact that we won't need to rely on the integrity of the borehole seals is a good result, because it is difficult to prove or demonstrate that borehole seals will last for the very long time of the repository performance period. Despite our finding that a poorly sealed borehole is unlikely to pose a risk to repository safety, all deep isolation boreholes will be carefully backfilled, plugged, and sealed. This concludes the summary of our analysis. I hope I was able to shed some light on the various issues related to borehole sealing and their impact on repository safety. Thank you very much for your interest. I will be happy to address any questions you might have.